welcome back. We're still working on our cereal box example, but the reason we're sticking with it is because, one, we're familiar with it, and two, because there are still some more different types of probabilities that we might need this binomial model to calculate. So as a quick review, if this is the distribution, and we say that we're looking at 5 boxes, the first thing we calculated was the probability of getting exactly 2 hallops. So that's the probability that x is 2, and we showed it using the binomial probability formula, as well as using this calculator speak, where we use Binomcdf because the probability that is being asked about is specifically the number of successes being equal to a particular number, in this case 2. And we saw that we got the same answer no matter how we did it. We then asked, well, what's the probability of getting less than 2 successes in those 5 trials? And that does change things a little bit because it's not equal to 2, it's any number less than 2. So the most straightforward way to answer this question, because this is an inequality symbol instead of an equal sign, is to use the Binomcdf function on the graphing calculator. And the only thing that was a little weird there was the fact that x is equal to 1, even though this number is 2, because for Binomcdf, you need to put the highest number that's not included. So if we want all numbers less than 2, that's 0 and 1. The biggest number is 1, so that's why we put the x equals 1 there. I also wanted to show that you could still use the binomial probability formula here and write that out. It's not too terrible for this example because it's only the numbers 0 and 1 for the number of successes that are included. So you just need to write out the probability formula for the number of successes being 0, which makes that 0, this 0, and this 0. Everything else stays the same as up here. And then add the probability that the number of successes is 1. So those 3 numbers become 1s. I wouldn't necessarily say writing it out this way is sustainable if this number is very large. You don't want to be writing out 5 or 6 terms of this. Although there might be a shortcut that we get to that you could do that. You don't need all the middle terms, just the first and last. I also wanted to show that Binomcdf, all it's really doing is taking Binomcdfs and adding them up. So if you were to type in this, which is exactly the same as the Binomcdf, but you're using PDF with 0, enter that in, get your probability, and then add that to doing Binomcdf again, but with x equal to 1, the sum of these two is going to be equal to this one. So by introducing Binomcdf to you, I'm just having you get it all at once instead of in little pieces. And this is a valid thing that you can do on a test or a quiz or an AP test as long as you write out all of the parameters so that we know what model you're using. So we know how to calculate probabilities that the number of successes is equal to a value or less than a value. And I did cover also if this is less than or equal to, then whatever this number is the one that goes here because you're including that number as the largest one. But what's the probability of getting at least 2 hallops in 5 boxes? At least 2. This is the last type that you can get. And for this particular question, based on what we already know, there are 2 main ways that you can answer this question. There's the easy way and the hard way. So just to be very clear, the only reason there is an easy way and a hard way for this problem is because the easy way is going to use something that we've already figured out. The hard way is if it was like any other question in this where this information wouldn't necessarily help. So you still need to know how to do it the hard way. But if you've got a problem or a situation like this where you're being asked several different probabilities, they might have something to do with each other, and at this point, that might help you out. The easy way to approach this problem is, first, let's write our probability statement. So instead of equal to or less than 2, we want the probability of what? That x is at least 2. So how do we write that as an inequality? Well, at least 2 is the same as 2 or more, so greater than or equal to 2. What if I told you you could find out the answer to that without using the binomial probability formula, or Binomcdf, or Binomcdf? You don't need any of that. You just need to pay attention to what we've already done. Can you figure it out? If you want to give yourself a sec, pause the video. I'm about to spoil it. Remember when we talked about events and their complements? If we have an event A, then A complement is everything that's not A. And if you take the probability of A and the probability of A complement and add them together, they have to add to 1. This could come in handy here. Because the probability we need, the probability that the number of hallops is greater than or equal to 2, is the complement of something we've already calculated. It's the complement of this, right? We're still looking at 5 boxes. That was the case for all of these. What are the possible numbers of successes you can get in 5 trials? 0, 1, 2, 3, 4, or 5. We've already calculated here the probability of getting 0 and 1. This is asking for the probability of 2, 3, 4, or 5. Together, they're everything. And they don't have anything in common. They're disjoint. So the easy way to calculate this one is to just take 1 minus this. My apologies if you paused the video and used the number that was here. It was off. I forgot this first 2. This is really 0.52822. So if we use the complement rule and subtract that from 1, we get 0.47178. My bad about that. Hopefully you had the right number in your notes, and that's what you referred to. What I write on this board may or may not ever be true. It's kind of like the lurking variable. Sometimes they, like mistakes, just pop up everywhere. So that is the easy way. And notice, you can only use the easy way if you've already done something that is the complement of what it's asking for. It does happen sometimes. That could be a multiple choice question on a quiz or a test, or the AP test. They could give you something like this and ask you for this probability. And if you know the easy way, you can save yourself a lot of time. That was really quick. But let's assume that you didn't already do this, or that this is asking like a different number or something, or maybe this is the only question that's being asked based on this setup. You can't use the easy way. So I'm going to call it the hard way, but it's usually like the normal way. Maybe it's just me. I always look for an easy way to do something. Like, it's nice to have the backup of using the binomial probability formula or using Binomcdf for this. But if there's an easier way to do it, I want to know what it is so I can use it when I can. But it's situational using this. This is the way you can always do it. So again, if we want to know the probability that x is greater than or equal to 2, then this is asking for the probability that the number of hallops that we get is 2, 3, 4, or 5, right? So I'll give you a hint. The normal/hard way still involves using Binomcdf. And I don't know if I've ever called the TI-84 stupid before. If I haven't, I should have. The TI-84 is stupid. All right, let's bring one up just so I can be mean to its face. Here we go. Okay, look how stupid it is. Look at its stupid face. Why is it stupid? Because the only functions that we can use on this calculator that will help us find this probability are Binomcdf or Binomcdf. If we want to use Binomcdf, we're going to have the issue here. Since we want 2, 3, 4, and 5, we would have to use Binomcdf 4 times and add all those together. Binomcdf allows us to only use this function once. But remember how Binomcdf worked in this case. This, if you type in n equals 5, p equals 0.3, and x equals 1, it's going to calculate Binomcdf for the same n and p, but with x equals 0 and x equals 1, and add them together. It always starts at x equals 0 and only counts up to the number that you put here. So how can we use Binomcdf to find this probability if we want to find starting at x equals 2? Because no matter what we put in here, n equals 5, p equals 0.3, x equals, no matter what number I put here, it's going to calculate Binomcdf starting at 0 and going up to the number I put here. But we want to start at 2, not 0. So what are we going to do here? Well, this is why the calculator is stupid. Binomcdf only works that way. We're not going to be able to use it like this to calculate this probability. What we need to do instead is think about this. Right? Not necessarily the fact that we've already got the complement, but we can get this answer using Binomcdf if we do this, but tell the calculator to find the complement of it. How can we do that? First of all, I'm going to erase what's here. Okay. Think about what we just said. What I just said. I like using the royal we sometimes. Sorry if that's annoying. We just need to calculate this probability, but know that what this is really the complement of that. So, we're essentially taking these two things and smushing them together. We need to take the complement. So whatever this probability is, it's going to be 1 minus the opposite. It's 1 minus this. If we type this in, it's going to give us the answer we want. But you have to remember that it's the complement and type the 1 minus first. Otherwise, you're going to get this. And that's not the right answer. Okay? So, I guess the point of what I'm getting here, what I'm getting at, is that if this is a greater than or equal to sign, you're going to have to take the complement of the opposite. Right? So if we want x greater than or equal to 2, we have to take the complement of everything up to 1. All right, and I'll summarize all the different possibilities in a little bit, but I do want to make sure that we can do this. So just to be absolutely sure here, by saying 1 minus, right there, I'm literally saying the first things you should type here are 1 minus, and then go to Binomcdf. Type in what you need. Trials is 5, p is 0.3, the x value is 1. And then paste. So you got 1 minus Binomcdf, just like you see here. Enter, and we get that 0.47178. Right. So I want to make sure that you're a little more comfortable using this method with Binomcdf with a probability like this. I do want you to know that it would have been a little different if this is just a greater than 2 sign. Everything here would be the same. The only thing that would change would be the x. If this were greater than 2, then that means we want the probability of x equal 3, 4, or 5. So we need to take 1 minus the complement, which would be everything up to 2. Right? So whether this is greater than or equal to makes a difference here, the same way that this being less than or equal to makes a difference. I'm going to give you one example based on this still that I want you to work on and see if you can get the right answer, just to make sure that this sinks in. Here is your example. What is the probability of more than 4 LeBrons in 9 boxes? More than 4 in 9 boxes. Right? So, it's going to work similarly to this, but obviously some of the numbers are going to be different. Notice we're talking about LeBrons now, not Hallops. And we're looking at 9 boxes, not 5 like we have been. So a lot of those values are going to change, but it's still the same idea. You're still going to be using Binomcdf. And it's up to you. Do you know whether you still need to use the complement or not if this is more than 4? So take a minute or two, see if you can come up with it. Not just the answer, but make sure you write out whatever you need to get full credit. All right? Because it's not about the answer, it's about how you get there. And we'll see you when you're ready. Okay. Did you come up with this so far? Right? So again, the very first thing you want to do for any problem that is about binomial probabilities, or really probabilities in general, is write out that statement. What is it you're trying to find? The probability that x is what? Here, more than 4, greater than 4. Not greater than or equal to. It didn't say at least 2, or 4 or more. It's strictly more than 4. So greater than sign there. If it's greater than or equal to, you're going to need to take the complement. Because here, you want, essentially, the probability of getting 5, 6, 7, 8, or 9 LeBrons. But using Binomcdf is always going to start at 0. But you want to start at 5. So, in order to do that, you need to take the complement of counting all the probabilities from 0 up to 4. Right? Because you want to start at 5 and you want everything that's the opposite. So, you're going to take the complement, 1 minus Binomcdf. We're looking at 9 boxes now, so the number of trials n is 9. The probability of success for LeBron is 50%, or 0.5. And the value we want to go up to for calculating probabilities, we want to stop at 4. Everything up to 4. So that's what we need to type in here. Let's do that. This is the fun part. 1 minus Binomcdf. Whoop. Trials are 9. P is 0.5. And the x value is 4. Is that what I got? Looks good to me. Wow. Really? I actually didn't know that. I came up with that example like right when I wrote it here. 0.5. Wow. That's crazy. Actually, it's not crazy. It's actually not crazy. This is a little beyond the scope of this problem. But if the probability of LeBron is 0.5, then suppose you made a histogram with the number of possible successes on the horizontal axis so our random variable is here, and the probability on the vertical axis. You can almost see me and the graph. Cool. All right. This would go from 0 to 9. And this probability would go up to whatever. I don't know how high they go. I'm just sketching this out. If the probability is 0.5, then it's just like flipping a coin, right? It's half heads and half tails. For any individual box, it's equally as likely for it to be a LeBron or not. So, it actually turns out, and you can see how this makes sense, the probability of getting zero LeBrons in 9 boxes is actually going to be the same as getting 9 LeBrons in 9 boxes. That's the same idea as if you flip a coin 9 times, you have the same probability of getting 9 heads as 9 tails. Super unlikely, but it's the same. So these probabilities would be very small. Okay? it actually works that way for all the numbers going in, too, on both sides. The probability of getting 1 LeBron and getting 8 LeBrons is the same, and it's a little higher. 2 and 7 have the same. 3 and 6 are the same. And 4 and 5 are the same. It's perfectly symmetric, right down the middle. So the probability of getting more than 4 is everything here. It's exactly half. 0.5. How about that? You got a little bonus lesson in there. Awesome. Okay. But for right now, this is just a nice exploratory extension. I really just want you to be able to take this question and be able to write this out and get the right answer. So let's do a quick review of what calculator function to use and what exactly you need to think about depending on the type of probability that you're looking for. So let's say you know, based on the setup for the problem, that you've got Bernoulli trials, so that you need to calculate a binomial probability. If you need to know the probability that the random variable is equal to a particular number, you're going to be using Binomcdf, and you just type in n, p, and x just as you understand it. That's this one. If instead you're asked for the probability that the random variable is somehow less than or equal to a certain number, you're going to be using Binomcdf for that, as long as you want to do it in the most efficient way. Again, you could do multiple Binomcdfs for these, but I don't recommend it. This is what CDF is for, right? But the value you put for x is different depending on whether it's less than or equal to or less than. If it's less than or equal to, then this value is the same number that this is, because you want to include all the probabilities up to and including that number. But if it's a less than sign, say you want x, the probability that x is less than 5, you only want to count up to 4. So whatever this number is, if it's 5, you need to subtract 1 and only count up to 4. Right? If you count up to 5, then you're calculating this, less than or equal to. So that really does make a difference there. The binomial probabilities for greater than and greater than or equal to are the toughest ones, because you need to remember to take the complement. This is another one of these concepts. When you're dealing with these, I don't want you to memorize these. That's going to lead to some serious heartache and confusion, because keeping all these straight when they're so similar is going to be very difficult. I want you to be able to understand and come up with these on your own, depending on the problem that you're doing. I want it to make sense why it is this way. Don't just memorize, right? If you want to know the probability that x is greater than 3, then you need to take the complement, because this is going to start above 0. You need to take the complement so you can start at 0. That's what Binomcdf does. But you're counting all the way up to whatever this number is. If this is the probability that x is greater than 3, this wants you to start at 4 and go up. So you need to take the complement of everything else. That's everything from 0 to 3. So if it's a greater than sign, these values are the same. That way you're taking the correct complement. If, however, it's x is greater than or equal to 7, then this is asking for the probability of everything from 7 up. So the complement is going to be everything from 0 to 6. So this number needs to be whatever x is here, minus 1, so that you take the correct complement. Again, if you try and memorize these, you're going to get them backwards, you're going to mess them up, it's going to be awful. You're going to hate me, you're going to hate statistics. I don't want that, okay? I want you to use your noggin so that when you are asked the probability of x is less than 2, or the probability that x is greater than 4, you know what to put in. You can make it make sense for you, okay? However that works. This is the way that I understand it best, but maybe it's something different for you. But don't try and memorize it. It's not going to work. All right. Let's move on to something else. Did I tell you there was going to be a pop quiz today? I didn't? That's fine. That's fine. Just get out a piece of paper. We'll just do the pop quiz right now. Go ahead, pause the video if you need to. You should have notes already, but if you don't, get a paper and pencil. I want you to take this quiz. Are you ready? If you don't have paper and pencil, this is not going to work. You're going to fail the quiz. It's going to be awful. Go get a pencil and paper. If you don't have one, let's take this pop quiz. Are you ready? Okay, here we go. The quiz is 10 questions. Okay. There's a trick, though. You don't get to see the questions. All the questions are multiple choice. Every question has an answer between A and E. Right? So the answer to every question is either A, B, C, D, or E. But you don't get to see the questions. But you need to take the quiz. So you need to number from 1 to 10 and fill the answers in. I don't care that it's unfair. Yes, we're going to grade this. Okay, go ahead. Answer the quiz. You have 2 minutes. Pause the video. Take no more than 2 minutes to answer these 10 questions. And then we'll go through it. Are you done? Man, I hope you did well. This quiz counts for 85% of your grade this quarter. I can't keep a straight face. I'm sorry. This isn't really a pop quiz, but I did want you to do this, so this is your last chance. If you haven't filled out the answers, do it right now, because I'm about to give you the key, and to not do it and get the key would be cheating. So our answers are, all right, here's your answer key. If you just guess C for everything, ooh, that's tough. You get a 0 out of 10 and you fail. You fail real bad. Bonus points if you could come up with a simulation for how I came up with these using a random number generator, because that's exactly what I did. It just so happened randomly that I got no C's and no D's, actually. I wonder how unlikely that is. Huh. Interesting. So many questions. But I want you to figure out how many you got right out of 10. Make sure you record that somewhere in your notes or on that paper. And we're going to use this as the basis for an example. This example has multiple parts, A through E. We're not going to get through all of them in this video. We're just going to set things up. So part A, well, before we get into the problem itself, let's define the random variable. What does our random variable represent here? So I had you do this. I had every other student that's watching this video, which should be everyone in the class, right? Everyone's done this. The random variable is how many problems you got right out of 10. Or I guess how many problems a random person gets right out of 10. Okay, so you might already be able to see some similarities between this random variable and the one from the last example with the cereal boxes. That random variable was the number of hallops in 5 boxes. This is the number of correct answers out of 10 questions. Part A. It says, can we use the binomial model to calculate the probability of getting certain numbers of questions correct? Students who are not going to do well in this unit would just say yes or no without providing an explanation. The answer is yes or no, but you need to provide statistical evidence for that answer. How do we determine whether a random variable can be binomial or not? What conditions do we have to check? We talked about 3 of them. For each trial, are there 2 possible outcomes? That's the first condition for whether something is a Bernoulli trial, which will allow us to use the binomial model. Do we have 2 outcomes for each trial? Well, first you need to know what a trial represents in this scenario. A trial is a single question. What are the possible outcomes for each question? correct or incorrect, right or wrong. So that condition is met. What's one of the other conditions for whether these trials are Bernoulli trials? Does each trial have the same probability of success? Well, first we have to define what a success is in this case, and that's a pretty natural thing to assign in this particular case because a success is getting a question right. That makes sense. I suppose you could consider a success getting the question wrong, but that would be weird. You could, but let's not, right? So is the probability of getting all these questions right the same for every question? Well, either you chose randomly. I certainly assigned the answers randomly. So what is the probability that yours and mine match, assuming there was randomness involved? Well, there were 5 possible answers and only one of them is correct for each question. So since all of them were equally likely, it should be 1 in 5, or 0.2. And that's the case for every single question. So they all have the same probability. That condition is also met. There's only one more. Are the trials independent of each other? That's the third condition for a Bernoulli trial, right? We need independent trials. Again, the trials are each of the questions. So is your response for this question independent of your response for this question? Is it independent of your response for this question? Well, assuming you didn't just go C, 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 then yes, right? At the very least, I determined these randomly, right? So at least on my end, the way that these are distributed, this one has nothing to do with this one. We've got 2 A's in a row here, 2 E's in a row, right? It's not like they always have to be different. So yes, each question is independent. So there can be some confusion checking this condition sometimes. What is it about the trials that we are asking if it's independent or not? It's all based on the random variable. The random variable is whether your answer is correct. So of course, whether you get this question right or wrong or this question right or wrong definitely is independent, if for no other reason than because the answers were determined randomly. Okay. So this condition is also met. So yes, there's a sentence you should write once you've checked all the conditions here. Okay, I'll admit, maybe you don't need to write as much as I did here, but once you check all the conditions, you haven't really answered the question yet. Why is it that you check these conditions? It's because to use the binomial model, you need to prove that the trials here are Bernoulli trials. So the answer is yes, since all the conditions are met. We make sure we put that right at the beginning. There's no confusion there. Since all the conditions are met that you've shown, each question is considered a Bernoulli trial, and therefore the binomial model is appropriate. There's no mincing words there. You even put some context in there, talking about what is the variable. It's based on the questions themselves. Those are the trials, right? So we check these conditions so that we could see if we had Bernoulli trials. Since we do, that allows us to use the binomial model. I want these ideas to be connected and not isolated. I don't want you to see this and be like, okay, check conditions, use binomial model. I want you to see why those things are connected to each other. You check these to see if you have Bernoulli trials. If you've got Bernoulli trials, then you can use the binomial model. Okay? We're going to continue with this example in the next video. It's got parts B through E. You can probably guess that we're going to be doing some binomial probabilities here, so it's going to be similar to the one that we did before. But you've learned a lot in this video. We learned how to calculate probabilities if we have a greater than or equal to sign. We take the complement. And now we're getting into this new example here. That should be exciting. So we'll see you in the next video. Have a great day.